Hey guys, welcome back to my channel, and in today's video we are going to solve one more LeetCode question, that is question number 513. Find bottom left tree value. So this is a medium level question and it has been asked by these many companies, Amazon and Microsoft, in last 2 years. So let's see what this question is all about. So in this question we are given a binary tree and we have to return the leftmost value in the last row of the tree. So if we see this example that is given, so this is 2 1 3, and in this tree the leftmost value in last row is 1. If we see another example, so in this example we can see this is slightly bigger tree, and in this if we see last row and leftmost value, then it's 7, right? So this is what we have to find out. So let's see how we can solve it using this example. So in this example, we can see that there are so many levels and the last row consists of only one element, that is 8. So 8 will be the answer that we will be returning. So how we can traverse this whole tree and reach this leftmost value? So for that, what I will be doing, I will be firstly coming up to this place and I will be checking that here at this point our depth is 0 and the leftmost value is 1, right? Now what I will do, I will go to next level. On this level I will increase my depth, right? I will increase my depth and I will check the leftmost value. So this is the leftmost value at this depth. Then again I will proceed and I will see if the depth is greater than the previous one. So right, this is greater and there is a value. So what I will do, I am at depth, I am at level 2 and the leftmost value will also get updated. Again what I will do, I will go to next level. I will go to next level and at this level as well I will do the same thing. I will check if the depth is greater than the previous one that I stored or I observed. So I will again update the depth and the value in that level. So at this level the greatest value is 6. So what I will do, I will simply update it here. Again I will do the same thing. I will go one level further and I will check if the level is getting updated, then update the value. So this is simply what I did. But if from code's perspective I have to look at this approach, what I am doing is I am traversing this tree and I am traversing its nodes. So left and right node. I will be checking both the sides of the tree because we don't know at the last row on which subtree we are going to get the leftmost value, right? So for that we will be traversing the whole tree and we will be traversing all the nodes as well. So parallelly I'll be calling the left child as well as right child, and in that manner we will be traversing this whole tree. So for this approach, what we did DFS, right? We proceeded with DFS and we updated the leftmost value depending if the depth is getting increased. And how we are identifying that the depth is getting increased? Firstly, we'll reach a node. We'll check if this node is having a value, then simply check our initialized depth and leftmost value. So at starting, what we can do, we can keep our depth as -1 and leftmost value as 0. So we will initialize our max depth and leftmost value with 0. After that, we will start traversing from root. So root is having a value, so we will firstly check the level. Level is 0 here. Level is 0. So we will update our depth first. So it will become 0 and then we will update the value with the leftmost value. So this will become the value. The current value will become the value, because if the depth is getting increased, then only we are updating the value, right? Every time we did that, if the depth is same, we are not going to update the value. So let me just clean this board and we will go through that algorithm which will help you to understand this whole procedure even better, because I guess till now you all must be bugged with this whole explanation, so I will try to make it a bit simple. So what we are doing is, we are doing DFS. Like, we can solve this question with BFS as well, but for this video we will concentrate on DFS, and maybe in some other video I will let you know how to do it. But at the end, both the approaches are of same time and space complexity, so we can focus on any one for this video. So for now we can focus on DFS. So we will start performing DFS on this tree for all the nodes. We are going to travel all the nodes, or we are going to visit all the nodes, but we are going to update our max depth and leftmost value only when the depth is getting updated. So what I'm trying to say is, firstly we know what we need to focus on. We need to reach the depth, last depth, or the last level of the tree. So what we can say, let's define a level equals to -1, because right now we hadn't started traversing, right? So for now we can initialize it with -1. Secondly, once we had defined the level, after this we need to find the leftmost value. So leftmost value for now will be 0. So this is how we initialize these two variables. Now what I'm saying is, let's start performing DFS on this tree. So we will come to this place. This is the root. At this place the level is 0, the depth is 0. So what we will do, we will check if depth is greater than level. If this is true, then what I am saying, update our value. So value will become the value of the node, right? Node's value. And this is how we are going to update it. So at this place right now, we know that depth is 0, which is greater than -1. So we will update our depth or level. So it will become 0. And the value will be equivalent to the value of this node, so it will become 1. Now what I am saying, simultaneously go for both the children. So we will call a recursive DFS on left child and right child. Again we will do the same thing for both of them. So firstly we will come to this place. We will check if the depth is greater than the one that we already stored. We updated our variables, right? So at this place we will check the level. So level is 1 here, which is greater than 0. So what we will do, we will again update the level. It will become 1. And as we are updating level, so we are going to update the value as well. So it will become 2. Then when we are checking for 3, what will happen? Here we will come and we will check, is depth greater than the one that we are already having? So it will go to this variable, level variable, and check. So it is not greater, it is equivalent. So what we will do, we will leave it as it is. So in this manner we are maintaining the leftmost value of that level in the value variable, right? So again we will do the same thing. We will proceed and do DFS on other subtrees. So here again same thing happen. Is level greater than the one that is already stored, already present? So yes, it is greater, so we will update it to 2, and this will be updated to 4. Then we will go to this place. Level is equivalent, so we are not going to do anything. Then we are going to go to these nodes, and when we reach here, what we will do, we will do the same thing. We will check if D is greater than L, then simply update it. So this will become 3 and 6, and for 7 it will check and it will do nothing because depth is same. Then again we will do the same thing, proceed further and come to this last level and again check the same thing. Level is 4, so we will update it and update the value. And at last we are going to return this value. So this is how we are going to perform DFS, and this is the simple condition with which we are maintaining the leftmost value. So now I guess this is better than the previous explanation. Things must be way more understandable for you all. So let's now quickly code the solution, but before that let me just tell you what's the time and space complexity of this approach is. So time and space complexity of this approach will be big O of n, both will be big O of n, because time complexity is big O of n as we are visiting each and every node, right? Because we don't know at the end which subtree is going to have the last leaf node. So for that reason we are traversing each and every level and visiting every node, and that's why time complexity is big O of n. And space complexity is big O of n because we are calling DFS recursively for every node, for every child node, right? So for that there will be a call stack, or recursive call stack. And in worst case scenario, if the tree is unbalanced and it's in this shape, then in that case the space complexity will be equivalent to number of nodes rather than equivalent to number of levels. So that's the reason why we are having space complexity big O of n. So now let's quickly code this solution, and we are again going to solve this in two programming languages. So firstly, let's define all the variables that we discussed. That firstly we need max depth. So we are using self here because we will be accessing these variables out of this function from our DFS function. That's why I'm using self, or you can even pass if you want those variables, but this is way more easier. So that's why I'm defining the max depth, and it will be equivalent to -1 firstly, then leftmost left. This also has to be in the same format, so I used it. Leftmost value will be equivalent to 0, and once these two variables are done, what we will do, we will call DFS, and inside it this will be self.dfs, and inside this what we are going to pass, we are going to pass our root, that is the node, and depth. So the starting depth will be 0, and after this, once this DFS is being performed, what we will be returning, we will be returning the leftmost value. So here we will be returning self.leftmost value. So this is for this function. Now we are calling DFS function, so let's define that as well. DFS, and firstly it will have self, then node and depth. And inside this what we will check, firstly check if this node is having value or not. If not, then simply return. And if depth is greater than self dot max depth, in that case what we were doing, we were updating max depth with depth and self dot leftmost value with node dot value. That's it. And after this what we were doing, we were calling the DFS function for node dot left, and depth will be +1 because we are changing the level, right? We are going one level further. So same thing we will do for right node as well, and at the end we will add a return statement, and that's it. This was the whole code. Now let's check if I hadn't made any mistake, then this should work. And yeah, this is accepted. So let's quickly code Ruby solution as well. In Ruby as well we are going to do the same thing. Firstly we will define those variables, that is max depth. So this @ in Ruby is going to act as the self that we use in Python. So this is for accessing the class instance. So this variable will be accessible after out of this function as well. So now what we will do is we will assign -1 and leftmost value. Today, why my hands are crippling. So after this, what we were doing, we were calling that DFS function. So DFS, and inside this we were passing root, and depth will be 0 for root, and rather than DFS it became def. And after this, what we were doing, return @leftmost value. So this was for this function. Out of this function we will define our DFS function, which will accept node and depth. And then inside this function we are checking return unless node. So this is checking whether node is having a value or not. If it is having a value, then check if depth is greater than @max depth. In that case, inside this if condition, update max depth with depth and leftmost value with node.val. And then outside of this if condition, again called DFS for node.left comma depth +1. Do the same thing for right, node.right and depth +1 and return. Now let's quickly run and check. This is also going to be submitted. Yeah, so this is also working and it is being submitted. So these were the 2 solutions and the whole explanation, and I hope this video was helpful for you all. And if it was, then don't forget to like, share and subscribe my channel, and I will soon come up with more such questions. Till then, keep messing with algorithms, and thanks for watching.